Hello. After discussing the electronic structure in solids, we will move on to the vibration of solids, that is the vibration of lattice, a quantum of which is called phonon. You have already learned in the classical and quantum mechanics the linear harmonic oscillator. Here, not that one oscillator oscillates, but the entire lattice vibrates and it causes a stationary wave in the solid as a result of that. And we will understand how that occurs in solid and what are the consequences of that in solid. What is the phonon, that is a quantum of that vibration, what kind of energy momentum dispersion relation the phonons have. All these things we will study now, and we will also try to understand its contribution to the properties of the material, that is the solid under question. Okay. So we will start with the vibration of crystals with monoatomic basis, that is there is a lattice plus only one atom in the basis. That kind of a crystal we will consider first. So if we consider an elastic vibration of a crystal with one atom in the primitive cell, there we want to find out the frequency of an elastic wave in terms of the wave vector that describes the wave in terms of the elastic constant. Here we assume that the elastic response of the crystal is a linear function of the force. We make this assumption because this is valid for small vibrations and this makes the mathematics a lot easier. That's the reason we make this assumption. And if this assumption holds good, then the elastic energy would be quadratic in the relative displacement. If we consider a set of crystal planes, so one plane is given like this. These are the atoms that I am drawing. Another plane is, say, here. I am drawing the atoms. These are the positions of instantaneous positions of the planes. We call this plane, we mark this plane with S. This is S plus 1, this is S plus 2 and so on. This would be S minus 1 and so on this side as well. So these are instantaneous positions of the plane. Let's assume that the planes would have been elsewhere provided there was no displacement of the planes. That means if there was no vibration, let's say the planes would be somewhere else and we can mark those planes with a different color, say like this. This is one plane. Say this is another plane without a displacement, and this is another plane without a displacement. In this kind of a situation, we consider only nearest neighbor interaction. We don't consider that this plane feels the interaction from this one as well. We assume that Sth plane feels the interaction only from S plus 1 plane and S minus 1 plane. That's all. This is for simplicity. So we would denote the displacement with U. This is not the coordinate, this is the displacement. And if that is the case, and if we consider the elastic constant relevant for this case, like spring constant, as C, we can write the force on the Sth layer as C times US plus 1 minus US plus C times US minus 1 minus US. So, it is the displacement of S plus 1th plane and Sth plane that matters. So, the relative displacement comes in here, gets multiplied with the elastic constant. Likewise, the relative displacement of S minus 1 and Sth plane that comes in here gets multiplied with the same elastic constant, because we are talking about the same material here, we are considering the same material here. That gives us the elastic force that this layer, Sth layer, feels. This expression is linear in displacement and it looks like that of Hooke's law. C is the force constant, and the value of C for a given material would be different for transverse and longitudinal waves. Now, if we want to write down the equation of motion of an atom in the Sth plane, then we can write it as m d2u dt2 equals C times US plus 1 plus US minus 1 minus twice US. This is what we see from this equation of force here, and force is just written as mass times the acceleration, m d2u dt2. So, what is capital M? Capital M is the mass of an atom. And we look for solutions with all displacement having exponential time dependence, that is periodic. So, we look for solutions with this kind of a time dependence. If this is the time dependence of u, then d2u s subscript should be there, dt2, this quantity can be written as minus omega squared us, and this equation, that is the equation of motion, can be recasted into minus m omega squared us equals c times, that is the right hand side of this equation, us plus 1 plus us minus 1 minus twice us. This is a difference equation in the displacement, that is u, and it has a travelling wave solution. What kind of a travelling wave solution? The travelling wave solution would be of the form us plus minus 1 equals u times exponential of is capital K A times exponential of plus minus I capital K A. Capital K is the wave vector for lattice vibration. We didn't write small k to distinguish from the electronic wave vector. These are phononic wave vectors because these are the waves of the lattice vibration. A is the spacing between the planes. In equilibrium. So A is the difference between this plane and this plane, something like that. K is the wave vector. So A is something similar to the lattice constant, which is very similar to what we have done earlier for electrons. Now we can write using this understanding so far, minus omega squared mu times exponential of is Ka equals c times u exponential of is plus 1 Ka plus exponential of is minus 1 Ka minus twice exponential of is Ka. This is what we can write, and now we can cancel u exponential iska from both sides. This part from here as well as within this and here. So this part gets cancelled from both sides. If we do that, we get omega squared times m equals minus c exponential of Ka plus exponential of minus Ka minus 2. This is what we obtain. And now if we make use of the identity, twice cosine of Ka can be written as exponential of Ika plus exponential of minus Ika. All of you know this. If we make use of this on the above equation, we will obtain omega squared, which is a function of k, can be written as twice c over m 1 minus cosine of Ka. This is what we obtain. And cosine function is a periodic function. So this will have unique values within a certain region, which we call the first Brillouin zone. The boundary of the first Brillouin zone lies at k equals plus minus pi over a. Now d omega squared dk, this quantity if we want to calculate, that is twice Ca over m sine Ka. Now if we look at the zone boundaries, this quantity is 0. Sine pi equals 0, sine minus pi is also 0. The spatial significance of Phonon wave vector that lies on the zone boundary, we will look at that now. Using trigonometric identity, we can write that omega squared equals 4c over m sine squared half Ka. And if that is true, then we can take the square root of this to find omega equals 4c over m square root sine half Ka. If we now plot this quantity as a function of k, what do we obtain? Let's say k equals 0 here, k equals minus pi over a here, plus pi over a here, and twice pi over a here. This is the k-axis, and in this axis we plot omega over 4c over m square root. Just for convenience, we take this one here. So this part would be just a sine function, sine half Ka. We will have the absolute value because we are taking the positive square root of sine function. So we can plot it this way. This would be the kind of a plot that we have. So you can see that at the zone boundary the dispersion becomes maximum. Therefore, at a maximum its first order derivative should go to 0.